Yeah, ladies and gentlemen, I have a hard job here because... Closer, okay, closer. I have a hard job here because that's the last talk, and I'm probably supposed to entertain you. Let's see how far we can go with that. And the topic of my talk is not directly or not related to computer vision, although some data sets from vision will appear here in the talk. It's more related to deep learning, but to some theoretical aspects of it, and mainly I want to argue here why it could be reasonable to go for stochastic neural networks. Let me give you a short overview over the contents in the talk. So I'll start with trying to motivate a little. I don't have a killer application. Now it's getting really... I have to eat? No, but it's extremely loud, isn't it? Yeah. So, in the first part, I will try to motivate why it might be reasonable to go for stochastic neural networks, even though we don't have yet a, say, killer application. And then I'll speak a little about one possible mathematical formulation of such stochastic networks, mainly in terms of belief networks or Bayesian networks. And then I will show you how to approximately propagate not only means of those stochastic units in the network, but also their variances through the network. And then finally show some applications with respect to dropout and batch normalization. Okay. So first of all, let me say that probably those of you who are in deep learning know the type of stochastic networks which are used in GANs or variational autoencoder. But that's not what I mean here. Because look, in GANs, you usually consider deterministic networks, which however map a random variable with a simple distribution, say a Gaussian distribution, onto a variable with a complex distribution, right? But the network itself is deterministic. Okay, there's slight difference between GANs, and in GANs it's really just a mapping, whereas in VAEs it's usually a mapping which gives you the parameters of that complicated distribution on the other side. But what I'm going to speak about here is a model where we assume that each node of the network, of the neural network is a random variable, a stochastic unit, if you want. So, meaning that, so if we, as usual, denote by axis xki the outputs of the unit in layer k with index I, right? Then its output depends on the output of the previous layer in such a feed-forward network, but randomly. So we have a probability distribution for the output of a particular neuron in the next layer, given the outputs of the neurons in the previous layer. And sometimes it's quite useful to represent the same thing. It's very often possible and useful to represent this probability distribution directly as a stochastic mapping. So imagine that this are the outputs of the neurons in the previous layer. Then we have the weights. As usual, I omit the biases because you know that we can consider them as by some additional input. And then in a deterministic network, we would apply some, say, element-wise nonlinearity, but here we add some noise. Right? So this Z here is a random variable, in that case additive, with some known distribution, and it's independent of those random variables here. So it's just like a neuron where you have some additional injected noise. And through that, the neuron becomes stochastic. All right? So why do we need such networks? Why might it be reasonable to have such networks and to consider them? Well, the first option is to go for randomized predictors. Right, so dropout appeared here already in one of the talks at least, and it's quite clear, so probably you all know what's meant by dropout, and if we consider its multiplicative version, so to say, right, so when we switch off neurons during training, then you can see it as some multiplicative injected noise, right? Just here the noise is additive, but imagine that you write a Bernoulli random variable in front of that f. And it takes value 0 and 1, right? And then it's just multiplicative noise, which is doing the dropout for you. Or the other variant could be to consider rather such type of neurons here, right? So stochastic networks with additive injected noise. And overall, we want to consider such networks as randomized predictors. Okay, now probably those of you who remember the contents of the course in pattern recognition, suppose you heard one, will say, hey, come on, why do we need a randomized predictor? We learned in the very first lecture that it makes no sense to use randomized predictors because they cannot be better than deterministic one. To put it more correct, for each randomized predictor, there's certainly a deterministic one which is not worse. Why the hell should we then consider randomized predictors? Now, yeah, the situation here is, or when you make such a statement, it's in principle true, but it presupposes that you can find the optimal deterministic predictor, right? But in the context of deep networks, we cannot. You probably know that finding the set of network parameters which is minimizing the empirical risk over the training data is an NP-hard task. So we have no way to find the really optimal one, right? And it might turn out that working with such randomized predictors gives you better learning results. Right, you apply the same learning scheme, both of them don't find the optimal one, but maybe the randomized version will find a better one than the deterministic one. So the task in that case, the task you have to solve goes as follows. So you have the output of your network, right? Then you plug this output into some loss. But now look, and then you have to average, so to say, over the training data. That's clear, and that gives you the risk. But now, due to the fact that our network is randomized and has those injected noises, you have, in addition to marginalize, to average over those noises, right? So in the simplest case, you can imagine here 0-1 loss or something, and then you have to average to compute the expectation over the injected noises, and then the expectation over your training data, and this gives you the risk which you want to minimize with respect to the parameters. I will give you here a very simple example. I just tried the following. I considered the MNIST data set, you know, right? A very simple data set, and I considered a relatively simple CNN to avoid any overfitting, and I just learned them, both versions of the predictor, right? The deterministic predictor, which is straight away, you know how to do that, and then I also learned a network with the same architecture but with randomized, with stochastic neurons as a randomized predictor, using basically trying to solve basically this task here, right? And what I'm showing you here is the robustness of the two versions of the network with respect to input noise, Gaussian blur, so if we just blur the image, the digit, and with respect to, and with respect to fast gradient sign attacks. So this, you heard about these adversarial examples. And so the blue line, the blue curves here show the robustness with respect to these different types of changes, of noises or blurring of the standard deterministic predictor, and the orange one the same for the randomized predictor. So we were not trying to apply some kind of specialized adversarial learning here or something, right? Just use injected noise in your units, and then learn it. Later on, I will tell you how to learn. It's as simple as standard backpropagation. How to learn such a network. So it might make sense. And then even beyond, of course, we would like to use stochastic neural networks for learning predictive distributions. So what do I mean by that? Usually you would say, imagine you do a semantic segmentation with a deterministic network, with a deterministic CNN, then the outputs of the last layer, which are pixel-wise softmax, are interpreted as probabilities, right? Usually you would say, okay, these are the class probabilities for the semantic labels in that pixel. Fine. But what about their correlation? What about their correlation across, say, neighboring pixels? Or imagine the following task. Let's say we take MNIST images and cover half of them. So we want our network gets as input, say, the upper half of the MNIST images and should reproduce the lower half. And then it's quite clear that doing it with the standard deterministic CNN wouldn't do the job. Right? Because if you see some circle in the top, then there are several ways to complete it, but in all of these ways, the outputs of the neurons are highly correlated, and you cannot model this with this interpretation of a standard deterministic network. So let's go ahead and try to make them stochastic. And the simplest version is to consider such a network as a belief network, as a Bayesian network, and the idea is quite old. So due to Neal, 92. So basically, your network, the layers of your network, these are the layers of your network, and then you have conditional distributions for the outputs in the first layer given the inputs in the input layer, and probability for the outputs in the second layer given the outputs in the first layer, and so on, right? And this in the end defines you a standard belief network. And the joint probability distribution for the outputs of the neurons in all layers given the input factorizes into the product of those conditional distributions here. As I already told you, there is a equivalent view which sometimes makes the considerations and maybe also the invention of approximate algorithms or something the like easier. There is an equivalent view. So instead of saying that we have instead of writing down the formula for this conditional distribution given for the outputs in the next layer given the outputs in the previous layer, we can model it as a latent noise variable model. So once more again, so the outputs in layer K are given as follows. You take the outputs in layer K minus 1, multiply them by the weights as usual, and then you add independent latent noise. This is a vector, so to each element, and finally you take your nonlinearity, element-wise. So that's basically the model. I'm just repeating here. So the z's are just independent real-valued random variables. This is injected noise, and f is the standard nonlinearity, whichever you're using. Simplest example is probably a stochastic binary neuron. So say just one neuron, it has input, it has weights, and it is binary valued, so h is the Heaviside function, and z is our injected noise. All right? And suppose we know the cumulative distribution function of that noise, right? Then it's quite easy to show that just this one-liner here, that the following holds: the probability for our neuron taking value 1, given the inputs, is, remember this is a Heaviside function, just the probability that this expression is greater than 0, and if you bring z on the other side, you immediately see the cumulative distribution function, or its expression which is defining this probability, right, is defining the cumulative distribution function, and if you know it, then you just plug it here. Say in particular, if z is logistically distributed, then its cumulative distribution function is the well-known sigmoid function, so you get up with this. So if you have a stochastic binary valued neuron with Heaviside function, and this noise is logistic, then this probability of the stochastic neuron taking value 1 is given by the sigma function of Wx. Fine. So let's say we are considering such type of models, and now we are facing the usual tasks, right? We want to learn the parameters of such models given some training data, and probably we also need to be able to propagate, to do the forward propagation through such a stochastic network. Okay, let me start with learning, because this is not the main part here, but just to give you an overview how it can be done. Now, first of all, imagine we are in this situation when we want to learn when we want to use such a stochastic network as a randomized predictor. So that's our objective function here. We had it already. I just repeated it here. And now we have to minimize this expression with respect to the parameters of the network, with respect to W. And then suppose that inside our network here, all the nonlinearities are differentiable almost everywhere. Differentiable. Let's say if they are smooth and almost everywhere differentiable, right? Then like, I don't know, sigmoid, ReLU, softmax, or something like this. Then we can simply do it by stochastic gradient descent. You know that you usually in the deterministic case use stochastic gradient descent anyway by mini batches. And now you just add one more, so to say, stochasticity in that gradient descent by simply sampling these noises here during the training. So in each training step, for each example, in the mini batch, you just right away sample those independent noises, then compute the forward propagation and apply backpropagation as usual. So technically, there's absolutely no problem in that. Things are getting maybe a little bit more complicated if you are after a predictive distribution, because then you usually have something like the cross entropy, which is called cross entropy, which is just the likelihood, right, of the outputs. And then, of course, this averaging over the noises appears in the logarithm of the probability. So you need here the output probability, and to get it you need to average over the noises, and this happens within the logarithm. So this average here goes into the logarithm, and then things are a little bit more complicated, but doable still. So if you are interested, just have a look at this paper here. There are many others. Okay, then as I said here, here we assume that all the functions here inside, all your nonlinearities, are differentiable, at least almost everywhere. Things are getting more complicated, of course, if you want to work with, say, binary valued neurons or some other categorical variables. Yeah, because then the nonlinearity is piecewise constant. It's almost everywhere differentiable, but it brings you nothing, right? Because the gradients are zero. So then you are a little bit in trouble, but fortunately there is a way out here as well. So the first observation is that when you take this expectation over the latent noise, then it smoothes those jumps in your nonlinearity, right? So imagine it as follows. So say here you have a binary valued neuron. Its nonlinearity is a Heaviside function, and then it has some input value plus, and this is shown here by this black curve, plus this noise, somehow distributed, and then you average over that noise, and that smoothes your initially non-smooth function and makes it like this dotted sigmoid here. So that's fine, but still, and especially if you are going for the predictive distribution and need to do it within the logarithm, you want to have a good stochastic gradient estimator, so an estimator which has low variance, and this is at the moment still active area of research, right? And again, if you are interested, have a look in those papers here. Last one from this year's ICLR. Okay, we were interested a little bit, so to say, in the other question, going to in the other direction. What can we do with forward propagation? Look, here these approaches do not require, so to say, any forward propagation beyond the standard one, beyond the deterministic one, as I tried to explain. But this gives you only the learning, right? But in the end, for instance, you want also to use such a stochastic network, say, in order to know how uncertain is the output. So I feed in some input, and I want to know the uncertainty on the output side, right? And for that, the latest, I need to propagate those uncertainties, those noises, through the whole network. And the question is how to do that. Oops. So once more again, I just repeated this picture, so recall, so we have the layers, and then we have these probability distributions, and altogether that defines belief network. And now we want to compute the probabilities for these iteratively for the layers of the network, given assuming that we know already the probabilities of the previous layers. And this is clearly an iterative task, right? You suppose you know the probabilities of the outputs in the previous layer, then you have to average over them what are this conditional distribution here. And this task is hard, because usually you have many neurons in the layer, so the number of configurations the number of configurations you have to sum over here is exponential. So you cannot do it right away. So we need some approximations, and yeah. Let me try to give you an overview of a typical approximation and the one we are also using. So first you assume you approximate this distribution here by a factorizing distribution. And if you take the KL divergence, and it's easily seen that the best possible approximation by a factorizing distribution is given in terms of the marginals. So we assume instead of this joint distribution, we write a product. Of an approximating factorizing distribution. And then you might, using law of large numbers, so if you consider the input of a particular neuron from the random, so to say, output of the previous layer, and if you have many neurons here in that layer, then basically you can approximate the distribution here on the input side as maybe as some Gaussian or some simple distribution. So if we make that, right, and approximate it by a member from some exponential family, say normal exponential or something, and then in the end it means that we need to compute only the moments. So, right, so instead of computing, so if we do that, then for propagating these distributions, it's enough to compute the moments of these marginal distributions, meaning means and variances. So in the end, the difference between a deterministic network and a stochastic network with regard to forward propagation is only that you are, in this approximation, you are propagating not just means, like in the deterministic network, but you're now propagating means and variances. And so it ends up by something we call moment propagation. Okay, the simplest approach would be to ignore the variances and to propagate the means only. And this goes as follows. So remember here you have so in order to compute the means of the layer K, you have to average over the outputs in the previous layer, and you have to average over the latent noises. All right, and especially this averaging here over the outputs in the previous layer is the complicated part. This is not complicated because it's factorizing, so to say, the noises are independent. And now the simplest approximation would be, so to say, just simply brute force carry over this expectation over the outputs of the previous layer into that nonlinearity function. Okay, that's brute force approximation. That's brute force approximation. But it gives you a simple technique, and then taking the average over the noises is usually not complicated because you know their distribution, and for all typical functions f, it's easy to compute here. This expectation is easy to compute directly. Okay, another option would be not to calculate it explicitly, but doing some sort of sampling. So just take several samples of noise, of all the latent noises, and collect the statistics from the propagating input plus the noise. All right, so you have your input, and then for the first layer you sample the noises and collect the outputs. You have the statistics, and then you repeat that through all other layers, but that's time consuming, of course. And so another and better approximation would be what we call AP2, approximation 2. And here we propagate really mean and variance. Okay, and now let me just show you so to say, the differences between these two approaches. So it's, as an example shown here, so imagine you have a network, so your standard layers, maybe convolutional, finally a softmax, and then your output node, okay, it's a categorical node here with 10, say, with 10 states, and then you take the very same model and just apply this AP1, and by that you estimate the means of the neuron outputs for all of the layers. And say for a particular neuron, it gives you the value here, you get just one value, and this is indicated here by this blue line. Then you make this sampling, and you get, for the very same neuron, and you get some distribution. You just collect the histogram, like shown here, right? And then you apply this mean and variance propagation, and you see this red curve. And what's quite interesting is that this simple propagation of means is very often quite off of the true mean. This comes somehow through those nonlinearities in your network, right? Whereas this AP2 approximation, which is propagating means and variances, is very often better. And then, of course, it also has an impact on your softmax output. So these are the 10 classes, say, right? And what you see here is the softmax output for the simple approximation AP1, again by blue, and then the sampling one, green, and AP2, the red one. Okay, how does this propagation of means and variances work? It's for the standard layers, it's quite easy and quite straightforward. So, say for a linear layer, yeah. So what? Suppose you know the expectations of the input of that linear layer, right? Then you can easily compute the expectation of the output, no problem. And with the variances, it is of course a little bit more complicated, but since we are making this factorizing approximation, so here in truth you would have the covariance matrix, and the outputs are indeed correlated here, right? But since we are making this factorizing assumption, it simplifies just to the standard, so to say, formula here, as if those x's were independent. Okay, and in the case of the simple element-wise nonlinearities, it's also relatively easy. So say for ReLU, this is your ReLU, and then you just take the already computed probability distribution of the outputs in the previous layer. You approximate it by Gaussian or by some reasonable, so to say, distribution, and then you apply this function, compute this integral, and you can do it, closed form. So in these things, I mean, we were not the first in that. There were quite a few similar results in preceding works. So to name some of them here. And so to say, the take-home message is that for all the standard nonlinearities, you can easily generalize your network and apply this mean and variance propagation. Things were a little bit less clear when it comes to categorical and max layers. So especially, say, in the output, when you apply a softmax, right, then, okay, you all know softmax, it's non-linear, but it's also multivariate, right? The input is a vector and the output is a vector as well. So then it's not so easy, and similar for max layers, say if you are doing max pooling and you want to propagate means and variances through a max pooling layer, then it's also less obvious how to do that. And that's our contribution here. We started with a softmax, and so the question is the following. So imagine that your inputs are, say, normally distributed, and then you apply a softmax, and then you want to compute the expectation in the output. The expectation of the output. And the key idea here is the following. You can imagine it as follows. Imagine that, in fact, you have an argmax. So you get an input vector, and then you have an argmax, which gives you a binary output, a binary vector, 0, 1 valued vector, right? So zeros everywhere, but in the place where the maximum is appearing. And there you get a 1. So it's so to say generalization of binary valued vector, but now it's multivariate. And the main idea here goes as follows, that if you have such an argmax and add to it some independent injected noise, in that case with a Gumbel distribution, then this argmax becomes a softmax after averaging over that noise. Right? This holds only if all these noise gammas here have the same mean and variance. However, for the real application, it's more complicated because the inputs, the outputs of the previous layer have different means and variance, and then one has to do something, and that was our contribution in the end. And so we found a reasonable approximation for this type of nonlinearities as well, and then generalized it to related problems like log softmax, which you need in variational methods, and also propagating mean and variance through max pooling layers. And by that, this story is complete. So now if you have a standard network with ReLU or leaky ReLU or softmax or whatsoever, all the standard things, you can propagate means and variances through that by using this, of course, approximative only. Yeah. Of course, we have checked the quality of the approximation, so it's a new approximation, and it seems that it reasonably approximates the value and the gradients, because in the end we also need to compute gradients, right? And the accuracy is comparable to sampling with 100 samples, roughly. So, okay, let's skip those curves. They are just showing this approximation quality, and let's go for some applications, for some simple applications. The first one we started to think about is replacing batch normalization by analytic batch normalization. So probably again you all know what batch normalization is, right? So for each mini batch and each neuron, you compute the statistics of that neuron and use it for reparameterizing its parameters. So it's depicted here. So you say you have a mini batch, and then you take a particular neuron, and then you just look on the statistics of that neuron, for the output of that neuron over the mini batch, and then you use your reparameterization so that the statistics after the reparameterization becomes zero mean and unit variance. That's basically batch normalization. But now, thanks to the approach we have, we can do this analytically, right? We don't really need to collect the statistics for all neurons in a mini batch. We can compute it over the whole data set. And this would allow you to decouple the size of the mini batches. So usually, especially, imagine that you have some task with really, really large images. And then you usually cannot afford to go for large mini batches. So you're forced to take small mini batches, but this makes the statistics you're looking for in batch normalization a little bit, high variance. But if you can compute the statistics analytically, you don't need it to collect it. You don't need to collect it from the mini batch. You just compute it analytically and use it then for the reparameterization. And so we did that. Yeah, so it's basically depicting this. So you have, so to say, your network and batch, and so in the standard way, so to say, you collect those statistics over the batches and then use it for this reparameterization in your layers. And here we are now simply computing using this mean and variance propagation to compute the statistics for the current weights of the network for all the neurons analytically, and then just plug it in here into the reparameterization. And indeed, if we use this method for training, so here we have no normalization, here we have batch normalization, standard batch normalization, and this is this method which is using this analytic batch statistic estimation. And so for training, it really gives something nice, so training becomes faster. But when we were looking then on the validation side, that it turned out that our method with respect to the final validation accuracy was worse compared to standard batch normalization, and we started to think about that, and it became clear, and I mean on a folklore level it is clear that the batch normalization introduces in itself some randomness into the learning process, right, due to the random selection of the samples in the mini batch. So, and this randomness somehow regularizes the learning. And if you compute these statistics analytically, you basically don't use the randomness of the batch normalization. And so we said, okay, let's try the following. We do our deterministic normalization, but then we, so to say, bring in the stochasticity here by some additional parameter noise into the parameters, and then we apply Bayesian inference, Bayesian learning. And the idea is quite easy. So this is a reparameterization for a particular unit in batch normalization. M denotes the batch mean, and S denotes the batch standard deviation. And then we just re-express it by plugging here the true mean over the whole data set, not over the batch, but over the whole data set, and the standard deviation for the whole data set, which we know or can compute, and then, so to say, repair it by these two terms, which are interpreted as bias noise and scale noise, and then we just apply Bayesian inference for estimating them, and then finally we get results comparable or better. We get results on CFAR using standard all-CNN. We get results comparable or better to other methods. So take-home message here: you can, if you are in need, if you want to decouple if you are working on large images and cannot afford large batches, then you can use that method instead, and don't have to think about the batch size, so to say, right? These things are decoupled then in the end. And then we tried the same for analytic dropout. So remember, I told you that dropout can be seen as injected noise, just multiplicative one. And again, we can model it, right, in the very same way. And we tried that again, we tried that again on CFAR, and okay, I forgot to write here the what's shown here on the axis, but that's the validation accuracy. Sorry for that. That's the validation accuracy here, and that's the validation loss. on CIFAR, and that's the training epochs, so to say, right? And again, we compare the situation when we do no dropout, when we do standard dropout, and when we do analytic dropout with our approximation in blue. So it learns faster as compared to standard dropout, and it is comparable. So if you do no dropout, then you see overfitting here. Again, this is loss, the validation loss, so you see overfitting here. But both methods, either standard dropout or these analytic dropout, so to say, prevent the overfitting as well, at least to some extent. And again, the results are slightly better, but in any case competitive for this type of for this type of network and this type of data. Okay, let me summarize. So I wanted to motivate the idea to use stochastic networks in deep learning, and this is, so to say, a picture which kind of shows things we have done. Oops, where is it? Things we have done already, like say statistics over the data set, initialization, faster training. But then it can be in principle used also for the situation when your inputs are uncertain. So if you have noisy sensors or missing data and you want to propagate this uncertainty through the network, it seems that stochastic activations like dropout give better generalization and better stability. This is still an open question here, how to do it well, including the learning for stochastic binary neurons. And then, of course, we also want to go towards generative models, semi-supervised learning, and more about Bayesian, and also more towards Bayesian learning, Bayesian inference. Thanks for your attention.
Questions, and I'll ask the first one. So in batch normalization with the analytic one, so you add your noise, how do you get the parameters of that noise, and how sensitive is to get these parameters correct?
No, okay, maybe it was a little bit confusing. In this analytic batch normalization.
Next, next. Yes. So the.
Aha, you mean, okay, so first in this simple version we were not adding any noise, right? We were just replacing the analytic computation. But now you are asking about this noise. Okay, we were not really learning it. Or we were learning it in this, let me say, in the standard way, like you do in Bayesian inference. So you make some assumption about the prior distribution for these parameters, like you do in Bayesian inference, right? So you make some assumption about the prior distribution over those parameters, and this we made somehow, and then you learn the posterior, like in standard Bayesian learning. Now, I don't recall really how we have chosen these the parameters for the prior distribution of those stochastic parameters. But up to that, it was. So imagine that you say, okay, imagine you say, okay, both these parameters are Gaussian distributed with some noise, and this is your prior distribution, and then you apply Bayesian inference, and you get when learning with the data, you get, so to say, the posterior distribution for these. Again, say, assuming they are Gaussian, but now with different means and variances for each neuron.
Next question. Okay.
Yeah, so I just wanted to ask, I think there might be a connection between what you were talking about and the recent Style GAN paper. So where they kind of, they looked at the generator architecture, and instead of propagating the random noise as input, they were starting with a fixed vector and kind of injecting noise at every layer.
Okay, I'm not reading too often GAN papers anymore, but okay, forgive me that. But for instance, in the context of VAEs, there's something called ladder VAEs, right, where you're also injecting noise, or at least into some of the. Somehow it echoes here somehow, but anyway, so where you inject noise, yes, and it's similar.
Next one.
Thank you very much for this very interesting talk. I just had a quick question on slide 16. Okay. I noticed that the learning rates are like slightly different.
Yes.
I was wondering what's the intuition behind this, and also like the overfitting of dropout, how this maybe also depends on choosing the dropout rate.
Okay, let me ignore the last question because I can't answer it. But the first one is easily answered. We just do some search over the first n epochs. And for each variant, try to find the optimal learning rate within the first epochs, and then use it for the rest. And that's why they are different.
Okay.
Okay. How could be injection of noise on a signal level, on the input level, be compared to noise on other levels? Because we are kind of just adding it on top on every layer, but we can just add it in initial.
Sure. I claim the following. Of course, it regularizes, right? If you inject noise only on the input level, it will already regularize. And I think the following will happen here with respect to these things, right? So this is robustness with respect to noise in the input. And of course, if I, during learning, inject noise in the input only, right, then the network will be also robust with respect to that noise, obviously. So, but I'm not so sure whether it will be also robust with respect to blur in the image and with respect to adversarial attacks, right? And so this is one answer. And the other answer is injecting noise on the input is a special case of this more general scheme, from the conceptual point of view at least.
And two more questions.
Thank you for the talk. My question is about independency of noise of neurons. As I understand, you consider them as independent. And have you tested this hypothesis on real networks? And maybe if they're not so independent, is it a good idea to account them as a covariance matrix, or maybe it will be better to make them really independent by adjusting weights?
Okay, maybe counter question. What do you mean by real networks? You asked me whether we have tested it on real networks. What do you mean by real networks?
Have you tested this hypothesis, and the noise is independent on neurons on already touched networks like LXNet, ResNet?
No, okay, we were a little bit lazy, so we were using. No, but wait. How can I test whether the assumption that the injected noises, this is a model assumption, right, that they are independent. How can I test this assumption on a deterministic network? So again, I'm not sure I really understand your question.
I think you always can convert a deterministic network into a random one by adding these components of noise to every layer.
Yes.
And then to check. Or maybe they're independent because of your method of training. And
no,
so
maybe
you apply this hypothesis of independence in the process of training. It's really independent.
Give me a sec. No. So maybe you confuse two things here. One thing is the injected noise. And we assume that this is independent for each neuron. Each neuron is a stochastic unit, and so to say, its injected noise is independent of the injected noises of the other neurons. This is a model assumption. All right? But maybe you're meaning this approximation here. That's indeed a different story, right? So here, when then propagating these noises, right, we are making this assumption that the outputs of the neurons in the layer are independent and can be modeled by a factorizing distribution. And this is a real assumption, and this assumption is wrong. This is a brutal approximation, right? And we were testing it, and we were testing its quality in deep networks, and we have seen that the approximation becomes worse and worse with deeper networks if you consider noise on the input side. So imagine the following. You have noise on the input side, and then you just propagate it, but in each layer you apply this approximation, this factorizing approximation, and then you see that the quality of your approximation as compared to sampling degrades with the depth of the network, right? And therefore, so far we were not really using it for learning networks with noisy inputs analytically, but instead we were using it for this. For these things I've been telling you, like this analytic dropout and analytic batch normalization, because in the context of them, the approximation is still quite okay, is sufficiently okay, right? But for other tasks, this approximation is still not okay because of this assumption, because of this simplification. But the assumption, on the other hand, that the noises, the injected noises are independent, it's just an assumption.
Thank you.
And we're your last one. Okay.
Do you want to? Oh, okay. Just a quick question. Thank you for the talk. So if we consider the case with just noise at the input, ignoring the rest, so one potential application I can think of is something we have done in CVPR 18, which is to train networks that are robust against that distribution at the input. So if you can propagate these moments all the way at the output, it would be nice to use a regularizer that says, I want the mean logit of that class, of the correct class, to be higher than the mean logit of all other incorrect class labels in expectation. And it would be also nice to minimize the variance of the correct class across that distribution. So you have an analytic formula that does that. Yeah. So, because, and also one more thing, which is, I think in that work as well, we managed to compute analytic expressions for the mean and variance of a block of layers.
I know.
Yeah.
I know that.
Yeah. Yeah. Okay. So
especially if I recall it correctly for ReLU, right?
Correct.
Yeah.
Or piecewise linear activations.
Oh, piecewise linear.
In general. Yeah. So maybe that also will improve the. We never actually investigated the case where there is injected noise at the layers, but maybe if you propagate blockwise, that will severely improve the approximation to some extent. And because in that expression, we have no assumption that the variance is output. So we assume that the output covariance out of each layer is actually dense, not just a covariance.
Yeah. Okay, thanks.
Okay, one more last question.
Hello. Thank you very much for your talk. And I'd like to ask, judging from your experience, if you were to speculate wildly, what area would you name would be, well, in the future, an area in which stochastic networks would be better than deterministic networks? What's your best guess? Thank you.
I'll tell you my wish, but I'm not brave enough to really say this is my best guess. I tell you what I'd like to do by using that, and that's basically kind of semi-generative network. So here. I want to let me put it with these words. I want to unify a typical VAE, variational autoencoder, which has two nets, right? This encoder decoder in one stochastic net, in just one stochastic net, which can be learned supervised and semi-supervised, and is regularized, so to say, through the stochasticity of the feedback connections. It would feature then also feedback connections, right? Not only feed forward. And those feedback connections would kind of do what we are doing when we are dreaming and regularize the learning. That's my dream. But whether it will work, I don't know.
Let's thank Boris again.